Good to go? All right. As this audience is almost certainly aware, cryptography is predicated on the idea that we can hide information behind some hard-to-solve math problem. Unfortunately, of course, many of our favorite classical problems for this purpose are efficient to solve with a quantum computer. Of course, discrete logarithms or factoring large numbers are traditional examples of this. But as a result, if we are going to maintain modern standards of cybersecurity, it becomes necessary to create new cryptographic schemes that can be implemented on classical computers while protecting even against quantum adversaries. And to this end, in 2017, NIST began what's been called the Post-Quantum Cryptography Standardization Project, with the goal being to come up with some basic slate of schemes that are kind of the best that we as a community can provide in these early days of quantum computing development. Now, in blue there, you see the schemes that have been proposed, at least many of the most high-profile ones, for public key encryption. Encryption basically guarantees that if you have some information, you can encrypt it, and only someone with the secret or a password or something like that can decrypt it. Over in orange, we see signature schemes, which will be more the subject of this talk. And a signature scheme gives you two guarantees. One, if you receive information, you know exactly who sent it to you. You cannot be lied to about the sender. And number two, when you receive that information, you know that it hasn't been modified since the sender originally sent it off to you. A case you might imagine is when you pull up a web page on the internet. You should know what server sent it to you, and you should be able to be confident that nobody has modified that page before you received it. And particularly here, we will be looking at CRYSTALS-Dilithium, which in 2022 was chosen as one of the standardized schemes by NIST to give us those two security guarantees, which it does, provided these three math problems are ultimately hard for quantum computers to solve. Now, the first two, module learning with errors and module short integer solutions, these are very standard lattice problems. As a general rule, if we believe that any lattice problems are hard for quantum computers to solve, then it will follow very naturally that these two are also hard for quantum computers to solve. The problem comes with that third one. Self-target MSIS, to the contrary, is a completely novel problem. It is produced by the exact structure that dilithium has, and it was never really studied in the literature prior to the development of dilithium. Thus, the big question in how well can we trust dilithium has always been, how hard is self-target MSIS? And the goal of this talk and the paper that it was based on will be to prove that self-target MSIS is ultimately at least as hard as MLWE. This allows us to prove the security of dilithium, to prove that it will give us those guarantees, that you know who sent you information, that it was not modified in transit, based upon two really trusted lattice assumptions, namely MLWE and MSIS. But before we can get into any of that, we are going to have to define a few algebraic structures, just so that you can understand the proof. To begin, here we have the ring RQ. This consists of all polynomials with a maximum coefficient q-1 and a maximum degree n-1. We can discuss the subset of these polynomials, which we will call the small polynomials. They must have an infinity norm, or really a maximum coefficient is what that is, of lambda. You can use other norms, but the original dilithium specifications choose the infinity norm, so we'll take the same. And finally, we have the subset of polynomials in RQ, which we refer to as short. These have tau coefficients exactly equal to 1, and the remaining n minus tau coefficients are all equal to 0. And to finish our introduction, we also need to discuss how hash functions change in a quantum setting, because this is, of course, a large factor. So on the left in blue, you see basically a classical hash function. It takes some arbitrary length bit string and it maps it to some finite sized bit string. However, once you are in a quantum setting, you must allow for the idea that an adversary could query a hash function in superposition. Thus, we get a structure like we see on the right in orange, which we could refer to as a quantum hash function, wherein you are allowed to make some superposition query and receive some superposition response. Now, any hash function will have to be realizable, deterministic, surjective by definition, but good ones will have several other criteria that we find useful, namely a resistance to attacks like preimage resistance and collision resistance. One additional consideration is that in the standard model, when we construct these hash functions, we trust that they have those good properties, preimage resistance, collision resistance, up to some assumption. You assume a given problem is hard, and then you can say this hash function is collision resistant. But as is often the case in classical cryptography as well, it is convenient if we can instead take basically a idealized version of these hash functions instead, and we call these random oracles. Basically, they have these nice properties, preimage resistance, collision resistance. By nature, we don't have to make some assumption that they have it. And this is especially useful for separating the study of, say, the security of a scheme versus the security of a hash function. You can kind of study those independently using these models. Classically, this is the random oracle model. In a quantum setting, this will be the quantum random oracle model. So all of our hash functions will be treated as quantum accessible. You can make these superposition queries, but they have preimage resistance and collision resistance just baked in. With those definitions in hand, we can now define the three cryptographic problems of interest: MLWE, MSIS, and self-target MSIS. In MLWE, you're given some operator with elements in the ring RQ. You're also given a vector chosen according to one of two distributions. It's either chosen uniformly from all the vectors in RQK, or it's created in this product form that we see here, where it's the operator times some, usually a small vector, plus an additional vector. These are sometimes also called the noise vector as well. And the question is, can you distinguish between whether the vector you have been handed is a uniformly random vector or a vector made in this shape that we'll refer to a bit as like an LWE sample? It has to take that form of an operator and an addition. And this is generally found to be a very hard problem to solve. The next problem on our list is MSIS. Again, we have a very similar operator with the same kind of elements, but now we are tasked to find some short vector such that the product of the operator with the vector is equal to 0. This is another problem that tends to be quite hard. Which of course leaves us with our novel problem, the one really in question. Self-target MSIS, like the other two, starts with an operator with elements in the ring. It also includes a hash function. And since we will be working in the quantum random oracle model, we will just take that to be a function selected uniformly at random from the set of all functions from RQK to B tau, which is that set of short vectors, if you recall. And here we have to find some vector solution where the first L-1 elements are small and the final element is short, such that the product of the operator and your vector hashes to the vector's final element. This gives it a almost cyclic structure in that your vector has to have the same information, some of the same information in it, that the response to the query has to have, which is a very unique kind of behavior. Now, in order to prove that this problem is hard, we will ultimately combine sort of three relatively recent technical developments in this three-step proof. First, we will show that solving self-target MSIS is at least as hard as solving something called the chosen coordinate binding experiment, which is generalized from a 23 result by Daochen and Spooner. We will then show that solving this chosen coordinate binding experiment is at least as hard as passing a collapsingness experiment in a result from Gendry. And finally, we will show that passing this collapsingness experiment is at least as hard as solving MLWE for a specific uniform distribution. starting with our first step in blue, we do need to talk a little bit about this random oracle that we're dealing with, as it is the source of a lot of the complications for self-target MSIS. That cyclic property is not easily done away with. Now, classically, we have options. Namely, we can do something called rewinding. And in rewinding, the idea is you have this query algorithm. You can run it forwards until it produces some output solution sigma. You can then rewind, returning to an earlier state and replacing your hash function with this new hash function we'll call h prime. And the goal would be to select h prime in such a way that the first I queries would all be responded to the same, regardless of which oracle you used. Then when you run it forward again, since it may or may not respond to the remaining queries in the same fashion, you can feasibly get out a second different solution from this query solver. And specifically, it can be shown in the random oracle model, which again is classical, that there's a probability of you getting this something like your original success probability squared. Now, this is very useful because for self-target MSIS, you can imagine if we can produce two solutions from the same query, then it's sort of like we start with this top line, where the hash of that nth query is equal for both your first solution and your second solution, both of these produced by this rewinding process, which means that you have this a.rc, the hash of that equal to this a.r'(c). And since hash functions are collision resistant, you ultimately go through these steps here and find a solution that is very obviously the MSIS problem. You have found some small vector r minus r prime such that the product of that with A is equal to 0. So classically, self-target MSIS is hard, but of course, rewinding is decidedly not a thing that can be done in a quantum setting. The idea of running a process forward and then returning to an earlier state would require you to either save the earlier state, violating the no cloning theorem, or it would require you to have a reliable means of taking that final measurement and then returning back to an earlier state without the measurement having perturbed it, which is also impossible. So instead, we are forced to look at other techniques, and largely more complicated techniques. And ultimately, what we landed on is something called reprogramming. Now, this can be used in the quantum random oracle model. And specifically, rather than trying to replace the hash function for the last n minus I queries, you're trying to reprogram it at usually a single location or some O of 1 number of locations. At which point, you're able to show that there's some probability of that reprogrammed query being the one that is utilized by the algorithm. And having reprogrammed it with some classical response, you're able to sort of separate your problem from the random oracle itself, and instead solve it based upon that classical query rather than the number of quantum queries that you would have made otherwise. Specifically, a result from Daochen et al. Demonstrates that you can create some simulator algorithm that is a quantum algorithm, but that is using just a single classical query with a success probability that is at least that of your original polynomial quantum query quantum algorithm over O of p squared, where p is the number of queries that was made. So in this way, we are able to simulate reasonably accurately any sort of large-scale quantum algorithm attacking self-target MSIS with a much simpler algorithm that is still quantum, but is only allowed to make this single classical query. Now, if you were to try to solve self-target MSIS using a single classical query, realistically speaking, there's only so many ways to go at it. First, you're going to select some kind of query. Maybe you select it in a very clever fashion, but you're going to have to pick one. And having done so, you get a response. And since we are in the quantum random oracle model, we can assume that this response is selected uniformly from the set of all short vectors, b tau. You then have to try to find some vector r such that rc constitutes a solution to the self-target MSIS problem by that product being equal to the query you originally chose. and R itself must be small. Now, interestingly, if you look at this structure here, while this is a very reasonable way to attack self-target MSIS using a single classical query, it also has a name. This is a somewhat known structure called a chosen coordinate binding experiment. Specifically, Dell, Egnall, and Spooner worked with a chosen bit binding experiment in their 23 work. And if you just generalize that out to a module setting, you get the experiment we've found here. And very usefully, we can then prove that that is at least as hard as something called a collapsingness experiment. Which, defining this, should generally be understood that an algorithm, B1, B2, passes the collapsingness experiment if it can create a register of any form. There are some validity requirements, but it has to create a register and then try to detect whether or not that register was measured in the computational basis. All collapsingness experiments take a form something like this. They've been actually showing up a fair bit in cryptography, and there's some thought that it might be a quantum analog of sorts to collision resistance. But for our purposes, it will just be an intermediary experiment that we pass through on our way to MLWE. And specifically, what we can show is that if you have an experiment that solves our chosen coordinate binding experiment, you can use it to construct registers over your query space, your vector space, your response space, and possibly some auxiliary memory that we'll just denote as an arbitrary length bit string. You can then prepare these projective measurement states, the pi, that basically checks whether or not your registers are in self-target MSIS solution states. And because there is such a strong link, really, between what kinds of small vectors you can choose and what kinds of responses from the hash function you can have that actually give you a functional answer, the result tends to be that if this is measured, if that b tau register is measured, it will tend to perturb the states in such a way that when you go back, you find you are no longer in a self-target MSIS solution. So as a result, while we are glossing over some of the technical details, if you can generally pass the chosen coordinate binding experiment, it will follow that you can pass this collapsingness experiment by detecting this computational basis measurement. And finally, we utilize a technique to show that if you can pass the collapsingness experiment, it follows that you can solve the module learning with errors problem, MLWE. And specifically here, if we consider our collapsingness problem, the goal is to identify that a computational basis measurement was made. So really, you're trying to distinguish between something like an identity operator, where no measurement occurs, and this computational basis measurement, which we'll refer to as MComp for our purposes. MLWE, by contrast, you are trying to distinguish between some random sample B that's just selected from the set of all possible vectors, versus a B that specifically takes the form of an LWE sample, so some operator times a small vector plus some noise, some error. But as it turns out, if you construct operators like so, where they select some B either from the set of all possible LWE samples or uniformly at random, select S from the ring, then make this partial measurement Y to by plus S with this special rounding function that basically just rounds your result into T equal spaced bins. The operators that result from this can then be proven to be very close to the identity operator and very close to the computational basis measurement operator. So these partial measurement M LWE sample and M RQK can be shown to resemble the operators that are distinguished by the collapsingness algorithm. So if you can pass the collapsingness experiment, it follows that you can distinguish between these samples and thus solve the LWE problem. So in conclusion, an algorithm that solves self-target MSIS with advantage epsilon from P queries would imply an algorithm that can solve the MLWE problem with a few minor changes in the parameters. And from this, it becomes feasible to talk about the concrete security of dilithium as well. I won't go into the technical details here, but what we are able to show is that if we compare our parameters, the ones that will result from our proof of the hardness of self-target MSIS, we do have some pros or some cons in that we are required to increase a number of the parameters in order to get the same level of security. But this was always to be expected. The original security reduction for self-target MSIS is a heuristic. So in order to rigorously prove it, it is not surprising that we result in some increases to the parameters. And the other sort of known formalization for dilithium actually requires dilithium to be moved to a non-native ring in order to prove its security. So while our parameters are larger than those suggested by this dilithium QROM, since we are on a better studied ring structure and a sort of more optimal ring structure, our algorithms still end up being more efficient to practically implement, requiring something like 2 times fewer integer multiplications and 3.5 times fewer integer additions. So we provide here the first proof that self-target MSIS is hard in the quantum random oracle model. Our version of dilithium, the security proof that we can provide from that conclusion, is provably secure under safer assumptions than the original dilithium protocol, and is more efficient to implement than any of the previously existing proofs for a rigorous dilithium. And I'd just like to acknowledge the University of Maryland, NIST, and QUICS, as well as my co-authors, Dr. Carl Miller and Dr. Daochen Wang. And I'm happy to take any questions you have.
Thank you very much for the talk. I hope this isn't a dumb question, but I was wondering if the security proof you just provided would translate well if we just used classical computational tools instead of quantum operations. Like if we only have a classical computer to do computations, can we prove something similar? Or
interesting question. First, there are no dumb questions. 2, I would say you could probably prove these similar results, but it wouldn't make a lot of sense to bother. Realistically, in a classical setting, you can use rewinding, which makes the proof of the hardness of self-target MSIS very quick and easy. It proves almost directly to be as hard as MSIS by that proof I very briefly covered here. Let me see. Here we are. And since it's harder than MSIS, you quickly conclude that dilithium is secure so long as MLWE and MSIS are hard, and you're done, which is a great result, but proving it in a quantum setting takes a little bit more doing.
Could you perhaps briefly say how the self-target MSIS is related to dilithium, or what the motivation was?
Yeah, I wish I had a better slide for it. I'm not sure I do. So when dilithium makes a signature, it takes kind of an LWE sample and a random matrix, and takes the operator, the random matrix, and adds the sample. And then when you're trying to actually confirm that by the verifier, it double checks that same hash. So it's trying to approximate this previous product you've constructed, and it has to match up to the response from this hash function, basically. So if you attempt a no message attack, so that means you're just trying to fool the verifier, you aren't actually using a signing oracle, you have to try to construct a small vector such that the small vector times A hashes to its own final element. So self-target MSIS directly results from the NMA attack. The CMA attack security is based on LWE, to my memory. I'm trying to remember exactly where you get MSIS. In there somewhere. But yeah, so it's just a direct result of if you try to fool the verifier with no other information, you will find that you have to solve self-target MSIS. And any Fiat-Shamir-based signature scheme of a similar form will end up with a very similar cyclic problem of this type.
Do you recommend any original reference for this topic?
Yeah, it's definitely a good idea to start with the specification. That will include all of the design details and how dilithium is structured. I would at that point probably recommend our paper if you want to look into how we proved self-target MSIS hard specifically. If you wanted to look more broadly at MSIS or MLWE, there are a number of lovely papers from Regev on the subject. I could certainly get you a list after the talk if you'd like.
Thanks.